Hello, scholars. Some quick reminders before we get rolling with some more tools we can use to take derivatives of functions more quickly. Remember that this notation, d dx, means take the derivative with respect to x of whatever's coming after. So if whatever comes after that symbol doesn't have x's in it, somebody is messing with you. If it has a different variable, somebody's messing with you. We're going to learn what to do about that later. But if you see d dx, whatever comes afterwards should be some function of x, and this notation means take the derivative of this. Other things, I'm going to use all those different notations for the derivative. So if I start with a function y equals x squared, we'll want to know that I might call the derivative y prime equals 2x. That's one of the rules you just learned, right? I might call the derivative dy dx. Same, it means the same thing. So this second notation just specifies the variable in the function I was taking the derivative of should have been an x until you're older. We'll talk what to do later. But so dy dx, y prime mean the same thing. So I'll expect you to use both notations. In this case, again, still 2x. Okay, so we know how to take the derivative of a constant. We know how to take the derivative of a variable raised to an exponent. There's not very many functions. Turns out by the end of chapter 3, we're going to know how to take the derivatives of all of the functions in the whole universe, I think, actually. So what do we need to know next? We can learn this rule that can help us take the derivative of a function that consists of two functions being added together. And the good news is it works just like you would hope it would. If I want to take the derivative of x to the fourth plus 12x, I can take the derivative of x to the fourth, which I know is 4x cubed. I can take the derivative of 12x, which I know is 12, and the derivative of that sum is the same as the sum of the two derivatives. So if y is x to the fourth plus 12x, then y prime, or dy dx, is equal to 4x cubed plus 12. So this derivative of a sum is equal to the sum of the two derivatives. That works if you have subtraction too. So the difference, the derivative of a difference is the same as the difference of the two derivatives. And so here's that next problem that's on your paper. Oh, look. So I have a similar problem here. If I want to take the derivative of x to the fourth minus 2x squared plus 2, I can take the derivative of each of those separate mini functions, each of those separate terms, and use addition or subtraction as according to the original problem. So the derivative of x to the fourth is 4x cubed. The derivative of 2x squared, the 2 comes to the front and multiplies the 2 that was already there to make 4x. And then the derivative of 2 is 0, since 2 is a constant. So I get dy dx equals 4x to the third, take away 4x. So those two examples I just did are different from the examples that are on your paper. So that first example that's on your paper at the top of page 2, where y is x cubed plus 4x squared minus 2x plus 7, try that one on your own, and then we'll do the next example together. All right, I got this next one. If g of x is 3 over the quantity negative 2x all raised to the fourth, minus x divided by 2 plus 1/4. That looks way more complicated. But you can use algebra to simplify this expression, to rewrite it so it looks like the sum and difference of a bunch of different multiples of x raised to an exponent, and then we're going to be able to take the derivative. So first step, I'm going to rewrite this. Those parentheses down there in that numerator, that negative 2x, has to get raised to the fourth, so I can simplify that expression first before I can recognize that as a power of x. So negative 2x raised to the fourth makes 16x to the fourth, but that was 16x to the fourth in a denominator. So instead of x to the fourth in a denominator, I'm going to write that as x to the negative 4. So I've rewritten my function 3/16 x to the negative fourth minus 1/2 times x. This is a pretty common notation. They like to use it on the AP test. It's important to be able to translate back and forth between being forced to think of that as division, x over 2. You can also think of that as multiplication. That's negative 1/2 times x plus 1/4. Now I can take the derivative of each of those separate terms. I can use the sum and difference rule to help me just piece back together my derivative. So to take the derivative of 3/16 x to the negative 4, that negative 4 comes down to the front to multiply. So I end up with negative 3 over 4. X to the new exponent is 1 less than the old exponent. That's how I get negative 5. The derivative of 1/2 x is 1/2. I have a subtraction sign here because I had a subtraction sign there. And the derivative of 1/4 is a constant. Its derivative is 0. So my final answer, g prime of x, negative 3/4 x to the negative 5th minus 1/2. This next one's a good one. All right, this next example, I have an equation. F of x is 4x cubed minus 6x plus 5. I want to find the equation of the tangent line. So what do I need to write the equation of a line? I need an ordered pair. I know my ordered pair is going to be 2 comma. How am I going to find the y? I'm going to put that y into my function as the input. Sorry, I'm going to put that x into my function as the input. So 4 times 2 cubed, oh goodness. 4 to 32 minus 6 times 2, 12 plus 5. Is that 25? And the other thing I'm going to need to know is the slope. Well, here is where we can finally use calculus, and not the long definition of derivative calculus. So I need the slope of the function f at the place where x equals 2. Don't try to tell me the slope of f at x equals 2 until you can tell me a formula for the slope of f everywhere. That's going to be called f prime. That's the derivative of f. So f prime of x, and I'm very serious that all of your work here should be very clearly labeled. If I'm about to take the derivative, then I have to give a derivative label to what I'm about to do. So the derivative of f is called f prime of x. F prime of x is that 3 is going to come to the front and multiply the 4, 12x squared minus the derivative of 6x is 6. The derivative of 5 is 0 because 5 is a constant. So now I have a formula for the slope of f everywhere. I need the slope of f at specifically the place where x equals 2. I'm just going to use my derivative rule, but everywhere I had an x, I'll replace it with 2. This is 12 times 2 squared minus 6. That's 12 times 4, 48. Take away 6 is 42. So now I have enough information to write the equation of my tangent line. I'm going to do it down here at the bottom of the screen. I'm sure you have more room on your paper. Y minus y1 equals the slope times x minus my x coordinate was 2. That's a fine answer. If you'd like to change it into slope-intercept form and that makes you happy, feel free to. All right, this is another good one, and it's way better than the problem that I crossed out to put it over. So how can I find all the points where the graph of y equals x to the 4th minus 5x cubed has a horizontal tangent? So now, this is the first time maybe we've had to actually translate language like this into, you know, how can I use what I know about derivatives now to answer this question? Well, what we want to recognize is that a tangent line, the slope of the tangent line is the same as the slope of the curve, which we said is the same as the derivative. So we want, if our tangent line is horizontal, tangent line is horizontal, that means the slope of the function must be 0 because a horizontal line has slope 0, which means my derivative must equal 0. So I'm about to find y prime, the derivative of y, and set it equal to 0 and solve an equation using all of my mad algebra skills. So if y is x to the 4th minus 5x cubed, which is the function and ended up on your paper, y prime is going to equal, the 4 comes to the front, the 3 is going to come to the front and multiply the 5 that was already there, 15x squared. Yeah? Okay, so that's good. That was calculus. That was taking derivative. Now we have to understand what we're going to do with this. We want the function to have a horizontal tangent. That means the slope of the function needs to be 0, which means the derivative of the function needs to be 0. I'm going to set 4x cubed minus 15x squared equal to 0. and I have to remember how to solve that. So you're going to have to dig back in here and remember a bunch of things that you learned in algebra to solve a polynomial equation, to solve an equation in which the degree on the variable is bigger than 1. Typically, your best bet is to factor. So we want to get a 0 on one side. We're using what's called the zero product property, right? The ZPP. I remember. I heard you guys have that lesson in pre-calc last year. So I'm going to factor. I already have a 0 on one side. I'm going to factor out a common factor, which in this case is x squared. That gives me 4x minus 15. So now that I've factored, I can write two separate equations. That means either x squared was going to equal 0, which means x equals 0, or 4x minus 15 equaled 0. That tells me that I'm going to come up here. X is equal to 15 over 4. If you show more steps when you solve that equation, that's fine. If you show fewer steps when you solve that equation, that's totally fine too. Just notice that we all have to come to a final understanding that there are two solutions to that equation. One is x equals 0, and one is x equals 15 over 4. So I wrote this problem, and I think that there's still this much more work to do to give a final answer. I was asked to find all points where the graph of this function has a horizontal tangent. I found two x coordinates where it happens, but I haven't named those points. To me, in this case, I interpret that to mean ordered pairs. So I am going to find two ordered pairs on this, this function. I know the x's. How am I going to find the outputs? How am I going to find the y's? I'm going to use this function rule. So I think the points are 0, comma. What do we think y is when x is 0? Oh, that's nice, it's 0. What do we think y is when x is 15/4? Sorry, guys. You'll be fine. So my other one is going to be 15/4, comma. Give me 1 second while I do all this algebra. I've decided this is a good time to remind you that on the AP test, your answers don't have to be simplified. So I present to you my second ordered pair. 15/4, comma, 15/4 to the 4th minus 5 times 15/4 cubed. And then one more problem there down at the bottom of the page. Don't fall into my trap. You know a way to take the derivative of a function that's a bunch of other little functions added and subtracted together. That does not mean that you know how to take the derivative of two functions multiplied together. So your only technique right now to find this derivative, h prime of x, is to rewrite that expression as the sum of a bunch of little different polynomial terms. So your first step, use multiplication, double distribution, or FOIL, whatever you happen to call it, to rewrite that multiplication problem as a sum and difference. So once I use those four multiplications, I get that h of x is 2x cubed minus 5x squared plus 2x minus 5. Now I can take the derivative h prime of x. This 3 comes to the front to multiply the 2 that was already there, 6x squared minus 2 times 5 makes the 10 times x. The derivative of 2x is 2. The derivative of negative 5, or the derivative of 5, is 0. So my final answer, h prime of x, 6x squared minus 10x plus 2.